Hello again and welcome. This will be part 2 where we're looking at the UNI-T UT61E Plus. If you didn't catch part 1, I damaged the meter while using this power amplifier here. And I asked you what you wanted to see me do with this meter. So I'd like to thank everybody who chimed in. And what I'd like to do is go over some of the comments that you had. So Will44 wrote, I think it would be worth it to replace the PTCs and see what's what. Stanimar wrote, one more for the repair for entertainment and educational purposes. Binary Agenda wrote in, please try to repair it. Can't help but think after seeing what you did to improve the last 61E, they should have paid you to advise them what to change on this Plus model. Dream Voyeur 67 wrote, hello again Joe, and thank you for that surprising update about the so-called improved version of the UT61 DMM. I was always under the impression that a new or improved model of a particular product should surpass its predecessor in every way. Well, so much for being an improved version. I think Dave hit the nail on the head. If you're looking at the value of the meter, I have to agree with him that I think the original UT61E was a better buy. It certainly has a few advantages over the original meter, but when you start looking at spending $100 on a meter like this, I'm expecting a little more out of it than what we have with this meter. Vince1 writes in, how not to blow up your Nano VNA. Don't transmit into it. Of course, I had made a video recently about this little pocket Nano VNA. I had seen a post from an amateur radio operator. He had connected this thing directly to the output of his radio, and of course he smoked it. So that's the comment that he's referring to. I made a video then on how not to blow these things up when you're using them. He goes on to say, kind of shocking that it couldn't even read the spec 200 megahertz at low power levels. Goose Gitter writes, it's like, oh, they killed Kenny again, from South Park. It's pretty good. Here's an interesting comment from DIY Electronics Addicted. If you're not a meticulous technician, then you can't afford to buy good things. You're happy with simple things, but can be used somehow. Why isn't this a great meter for simple people who can't afford to buy expensive electronics? I didn't say it was, didn't say it wasn't. It's very rare that I'll give a recommendation on what people should buy and what they shouldn't. That's really your job as a consumer to decide what products are going to fit your needs. Again, to be clear, I'm not here trying to sell meters. I'm not a distributor. I have nothing to do with the multimeter industry. Now, personally, if I were looking at a brand new meter for my own use, of course I do a lot of electronics, I would hands down take this BM789 over this UT61E Plus. Yeah, this is about double the price, but it's by far in a different class. Pyromen 321 writes in, wow, that input protection got nuked. It did. Now I'm really curious how a stock UT61E would handle the transients, because there are clearly some significant differences between the new one and the old one. 6string63, sorry for wasting your money. I was one of the people who had asked you about doing it. You know, it's not really a big deal. Again, this is supposed to be one of their latest meters. I think a lot of people are curious how they improved it or if it basically stayed the same. He goes on to say, I can't believe that power amp roasted those PTCs like it did. How many watts were you pushing it to get it to read that higher frequency? I think when I started out, I was pushing it to about 20 dB or roughly 3 volts. That was before I started adding these amplifiers. But again, I didn't have a watt meter hooked up to this, and it's going to be load dependent. And of course, what we had done is connected the output of the amplifier right into the meter. Nothing was terminated right. I mean, who knows what was going on with that thing. Can't tell you that amplifier, that's not like, 10 kilowatts or anything. You can see it's quite a small amplifier. I actually constructed this amplifier from a kit. Somewhere up on the EV blog you can find where I was putting this together. So I had to machine the heatsink and whatnot. I knew I was going to be using this for lower power, so it doesn't have a heat spreader in it, and the power supply itself doesn't reach the voltages that this amplifier would have required to reach its maximum power. So it's fairly limited as far as how much power I can actually get out of this. Again, I built this amplifier for lab use, so it's not something that I'm using to talk with over the air. John McCormick writes, take a shot, see if you can fix it. What do you have to lose? Yep. It's kind of the way I see it. Gadget Review videos writes, you popped it. So referring to photonic induction, I happen to be one of his longtime followers. ChrisGrossman.com writes in, fixing it would be interesting just to see what failed. However, I agree further testing would no longer be valid. I think that's really my biggest concern. If I go ahead and fix this meter, what's going to end up happening is the fanboys are either going to say, oh, it failed because of the repair work that I did, or if it does really good, they're going to say, look, this is a great meter. Go out and buy it. It reminds me when Dave at the EEV blog had sent me that 121GW prototype meter. I made it very clear in the start of each one of those videos and throughout them that that particular meter was a prototype. You would think that there would be no confusion about that whatsoever. Of course, I ran some fairly extensive tests on that, and what ends up happening is everybody and their brother is confused. They're all considering that meter a production meter. It wasn't. And of course what I ended up doing was pulling all those videos down to avoid future confusion. But unfortunately, that's what we're dealing with. And I can believe that we're going to see the same thing with this 61E+. Chris Holt wrote in, he says, you had reasonably high level RF right next to the meter. Do you think that may have contributed to its demise as well? Of course, you know, I had the amplifier, again, sitting right next to the meter is what he's talking about. But again, everything is shielded. The idea of this amplifier isn't to radiate from the amplifier. It's basically to get the power down to the end of the cable. So no, I don't believe that having the amplifier sitting next to the meter has anything to do with it. I believe the damage was caused because I'm injecting that RF directly into the front end of the meter. Tintin writes, Joe, the meter terminator. Come with me if you don't want to live. Unitrend, please no. Joe, I'll be back. Jeff Garland writes, ha ha, if only UNI-T hadn't made a false claim about the frequency range that you just had to test. I was hoping to see if the meter could stand up to any transient tests. It died too quickly. And just to be clear, it was certainly not my intention to damage this meter that fast. I was thinking, you know, hey, it's a 200 megahertz counter. I'm just going to creep up on this thing. I really expected at some point it would actually start reading the frequency. And it wasn't until I grabbed the side of the meter I realized that it was overheating. By that point it was way too late. Alex Lavoie maybe? I don't know, sorry if I got it wrong. Just repair it. What do we have to lose at this point? Yep, I agree. KWPC Tech writes, can you see the values on the other PTCs? No, there was nothing left of them. It burned the outside right off of them. Basement Science writes, so what amplitude was going into that meter at the end? Do all your other meters handle that? I kinda doubt it. I can't imagine a PTC on other meters would be much more reliable at high frequencies. Maybe it could have read a 200 megahertz square wave instead of a sine. Now he brings up a really good point, and I think I'd like to spend some time going over that. So the front end of this meter goes into a PTC, and then to a second PTC, and then to a MOV, and then to another MOV, and then this goes back to the common point. This is going to go through a switch, and then on the output of this switch there's going to be a high-speed clamp, and then this is going to go on to maybe some current limiting, and eventually it's going to make its way to some kind of an IC chip. So this is very common for all meters that I look at, except for the front end, and Dave went over that. This is what we're talking about. So you can see here's our input lead. It goes to this surge rated resistor. So these are going to be flame proof. They're actually made to handle the IEC standard, and you can see it's in series with the PTC, and then it goes into the MOV, and we typically have two MOVs in series. So if we look, there's another leg that's just like this on the UNI-T. So you have two more PTCs and another MOV, and that MOV ties into this junction here. Basically the idea is that we're trying to get the voltage up, so the MOVs are typically rated for, I don't know, 700 volts or something. You want it to break down something just over 1,000 volts normally. So one of Dave's comments was, you know, why would they have not put in the surge rated resistor rather than just using two PTCs in series? I'm not really sure, but I can tell you that the UNI-T UT181A that I tested, that also has two PTCs in series. So it's a very similar configuration. You know, of course, I put that meter through a battery of tests after I blew it up with the grill starter and repaired it, and then found what was really wrong with the stupid design. Anyway, after that, I beat the snot out of that meter, didn't have any problems with it, and I had checked the frequency counter function for that meter, and there's a big difference between this meter and that meter, and that's when you look at the manual for that meter, it calls out 60 megahertz. And when I tested the meter, it goes into over range. It actually says it right on the screen that that meter's out of range as soon as you get over 60 megahertz. So there's no reason to test it at higher frequencies. That's the upper end of it, that's where they spec it, and that's where the meter works. So on the EV blog, again, somebody had asked about the voltage coming out of the amplifier, and they brought up basically saying that the manual had a derating number on it. And of course, if you download this manual off of the UNI-T website and you do a search, look for the word derate, you're not going to find it. But I believe that this is what they're referring to. So we have the frequency input amplitude. We can see for less than 100 kilohertz, they have a 200 millivolt RMS to 20 volts RMS. So what he's saying is that this 20 volt RMS is the derate, that you can't exceed that number without damaging the meter. I don't believe that that's what that means at all. I believe that this is the threshold for this meter to actually read the 100 kilohertz range. Of course, the manual isn't clear about that, but as we move up in frequency, you can see above 40 megahertz, it's not specified, and I believe the reason for that is that threshold probably changes quite a bit due to the roll-off of the meter, so it may require a much higher voltage than 20 volts to actually trigger it up. But essentially, I think what they're saying here is when you're using that frequency counter, the range on that input is going to be pretty wide. I also want to point out, if we look at the range right here, you can see 220 megahertz, and again, I believe that that's what they're showing on the box right here, that is the frequency counter input. One of my responses to both of these gentlemen is that, you know, if UNI-T has a problem with me testing at the 220 megahertz, you know, don't advertise that the meter can do it, and I'm not going to test it up there. So it's just as simple as that. So again, these are PTCs, and some of the designs will use a surge rated resistor that'll be in series with a PTC. And the question becomes, would a meter that's designed this way versus one that's designed this way, would it have any difference at all when it comes to testing these higher frequencies? And I'm saying yes, it would. We're going to run a little test, and we're going to use a couple of parts. These are certainly not what's included in that 61E. These are a standard 1K surge rated resistor. These are the MOVs that I installed in that UT61E that I modified. And these PTCs, yeah, these were made by Epcos. Those are a 5mm device. I think these have a breakdown voltage of 500 volts maybe. And I believe that the resistance for these is going to be roughly 1.3 k ohms. So let's have a look. Yeah, 1.4 k. And of course our surge rated resistor, which you can see is a 1K, is 1K. So in this case, we have a 1K resistor. Now, again, it goes to this high-speed clamp, and if you watch the video, I had that clamp engaged when we were running the test. So for all practical purposes, let's say this is a short, the switch is closed. So with this being a short, we've basically taken the MOVs out of the picture. Of course, to be clear, when we're talking about these kind of frequencies, everything's going to come into play. Everything's got parasitics. There's inductance, capacitance everywhere. And I believe that that's the reason that, you know, a more typical meter like this would survive a test hooked up directly to an amplifier like this versus this UT61E. So we're going to be using this exact VNA to characterize these components, and I think you may find it interesting. This is going to be our setup. You can see I have nothing more than a piece of breadboard, and then of course up here we have the Nano VNA. Channel 0, which is our output port, goes directly to this cable down here to our breadboard. On the other side of the breadboard, you can see I have another connector that runs back to this side of the common mode transformer. The other side then going on to channel 1 of the network analyzer. So what we're going to be doing is measuring this breadboard as a through component. So the signal goes out through the transformer and back in. And the reason for this transformer is to break the ground loop at lower frequency. And I made a video on how to use this network analyzer for doing PDN measurements. If you're interested in knowing more details about how this works, I recommend you watch that video. Or in general, if you're interested in PDN measurements, I recommend you turn to the internet because there's a lot of information about that subject out there. The last time I used this, we were measuring these components here. And here I have a 10 ohm resistor. Okay, the first thing we're going to do is run the software for the Nano. Again, this is something that I wrote, but it is publicly available. And it's asking for our default setup file. We'll go ahead and select that. And this is looking at the software. What we'll do is go ahead and turn on the network analyzer. You can see what it kind of looks like. Now when I use the software, I don't really pay attention to the screen. Let's go ahead and we'll select link. And let's give it a start frequency of 20 kilohertz. And we'll sweep it up to, let's say, 50 megahertz. And I'll go ahead and select the sweep button. And let's just set this thing to transmission. And you can see it's reading roughly 10 dB down, 11 dB down. Because of the type of measurement that we're going to be performing, most of the data is very feature rich at lower frequencies. What I'd like to do is run a log sweep, and this software that I wrote is actually capable of doing that. So we go ahead and select log, and now we can do segmented sweep. So we just select this button here, and you can see the lower part of the screen, it's saying it's sweeping between 20 kilohertz and right now 31 kilohertz. Again, this is basically our setup right now. We have port 1 going to the one side of the breadboard, which is essentially right now just a jumper, shorting it across, going to this common mode transformer. This is really nothing more than some coax wrapped around various toroids, and then that returns back to port 2. And again, normally if you're making PDN measurements, you'll add DC blocking capacitors to prevent the DC of the PDN from coupling directly into the network analyzer. Okay, you can see it's completed its sweep. Overall, the signal is fairly flat. Looks like it goes from roughly 10.6 dB down to about 11.22. What we're going to do is normalize this data, and the way we do that is just select reference, and then we select channel N minus ref. So if I were to repeat the sweep right now, this is going to give us a flat line at 0 dB. And you can see it's very close to 0 dB all the way from 20 kilohertz up to roughly 50 megahertz. So what I'd like to do now is select the Advanced tab, and we're going to select Bode plot. And what I'm going to do is select ohms. And now what we're going to do is take this little 10 ohm resistor. I'm going to place that from essentially ground to the signal path. So again, we have a piece of coax here. So what we're doing is putting our 10 ohm resistor from this signal path to the ground path. Normally we would call this a shunt through measurement because we're measuring the resistor as a shunt, but we're measuring through between ports 1 and 2. Let's go ahead and run a sweep now. And there we have it. So you can see this resistor is fairly close to 10 ohms all the way up to 10 megahertz. Starts to go a little bit inductive, maybe around 11 megahertz, 10 megahertz or so. But overall it's fairly stable. If you watch the video where I was making these PDN measurements, you may remember I cut the leads off of all these parts, and I demonstrated what effect that had on the measurement. Of course, the longer the leads, the more inductance. So let's just start with this 1K ohm surge rated resistor, and let's see what that looks like. And we're going to also place this directly across the signal path to ground. You can see it's reading fairly close to 1K ohm. Pretty much what you would expect. Again, we've got all these nice inductive leads hanging out here. But you can see overall the part is fairly stable. Let's go ahead and we'll save this to memory 1. Now let's have a look at a PTC. Again, we said this is roughly 1.4 K ohms. But notice we're at 100 kilohertz and it's already starting to dip. It looks like they're converging right at about 400 kilohertz. And now the resistance of the PTC seems to be lower than our 1K ohm resistor. You think this is getting hot? It's not. We're not putting any power through it at all at this point. You can see it's all the way down to 700 ohms and continuing to drop. And you can see as we move up in frequency, up at 50 megahertz, The impedance of this device is very low. Let's go ahead and save that to memory number 2. Now again, the UNI-T meter uses 2 PTCs that are placed in series. Let's go ahead and do that. So again, we just have the 2 in series going straight across. So we expected that the impedance of this is basically going to be double. Of course, we have the lead inductance, so there's going to be a little bit of difference. Let's go ahead and run a sweep. So while at the lower frequencies, the PTC has a much higher impedance than the resistor, as we move up in frequencies, it's much lower. So what's going to happen is, of course, lower impedance, it's more load on the amplifier, it's going to dissipate more heat. So again, you can see, even with the 2 of them in series, with all that added inductance, the impedance of those 2 are much lower than our single surge rated resistor. Let's go ahead and we'll save that into memory 2. Let's take our surge rated resistor and we'll put that in series with one of the PTCs. So again, here's our signal path. You can see going to the PTC in series with our 1K surge resistor, which is going back to the ground side of the breadboard. Now let's see what this looks like. Again, you can see we are up at about 2.1K. Of course, there's about a 400 ohm difference between the PTC and the 1K ohm resistor. And we can see at these higher frequencies, the impedance remains quite high. So again, let's think about this. We said the clamp is essentially a short. So basically we have these 2 PTCs tied directly back to ground. And we said that the impedance of these is decreasing as we're going up in frequency. So essentially these become a short. So what do we have is essentially a short going right across our amplifier. In the 1K ohm resistor, the impedance of that remains quite stable. So in this case, what we have is a PTC that's shorting, but it's in series with a 1K ohm resistor, which is quite stable. So the equivalent circuit is essentially a 1K ohm resistor. Hardly much of a load at all. For a few of you, hopefully you get an idea now that maybe all these meters are not going to behave the same when hooked up to that power amplifier. So again, I have this Brymen BM780 series meter. Again, this meter is non-functional, so I really don't care about it. What I'm going to do is I'm going to short directly across these MOVs to the return path. So again, for the Brymen, we have the 1K ohm surge resistor in series with the PTC, and there's 2 circuits just like this, and we're going to be taking this backside right here. We're going to bypass all of this, and we're going to go straight back to ground. Here you can see I basically have this braid going right from the common to the back side of the 2 PTCs. So we're expecting this to be somewhere about a K ohm or so. And there you have it, so roughly 1.3 K ohms. Alright, so I have my power amplifier off on the left. Again, this is connected directly to the input of the Brymen prototype meter. Again, one of the reasons that I like the BM869S is that it has 2 thermocouple inputs. I have a thermocouple attached to the top of each of the PTCs. I currently have our RF generator set for about 140 megahertz, slightly over where we damaged the UNI-T UT61E. Of course, the impedance of the PTC should be lower as we go up in frequency. What I'll do now is go ahead and start to increase the power to the input of the amplifier. Again, it's hardly breaking a sweat. Pretty much what I would expect. Again, at these frequencies, we're talking about essentially a 500 ohm load or the 2 1K ohms in parallel. And again, that's assuming that both PTCs are dead short at this point. They certainly are going to have a very low impedance. So I think all that's happened with the UT61E is, again, we have the 2 PTCs in series and their impedance gets lower as we go up in frequency. Of course, at 31 degrees Celsius, we're nowhere near the temperatures that are going to cause any kind of a burn. As a matter of fact, I mean, I can't even feel that. Let's try pushing our leads a little tighter to the parts. You see it makes some difference. But yeah, they're certainly not hot enough to where it's going to reflow the solder again. I solder at about 320, 340 degrees Celsius. You know, we're 10 times lower than that. So yeah, this is not a problem. So yeah, I'm going to go out on a limb and say that the majority of the meters that have passed my test that use this type of configuration with the surge rated resistor in series with the PTC probably would not have a problem surviving a test like this. Having a closer look at the meter, we can see that Q7 right here is cracked. It also appears that Q9 as well as Q11 have been damaged. These appear to be transistors. They are marked Y1. You'll notice right here, that's a little bit of solder that's came off of this lead. See, this PTC was getting ready to come out as well. One of the leads is already lifted. I think to repair this, we're looking at a minimum of changing out all 4 PTCs. Obviously, these clamps up in this area are going to have to be replaced. Of course, the circuit board's going to have to be cleaned. But I don't see any other problems really with the meter. I think the real question is if we've damaged any of the ICs. Hopefully these high-speed clamps have saved those. This is the one PTC that fell out. And as soon as I touched the one lead, it fell off the part. I believe the black here is the shrink wrap, or essentially what's left of it. This would have been originally over the top of this component. Again, all that will need to be replaced. All right, the first thing we're going to do, let's go ahead and pull out some of these parts. So we'll start with the PTCs. As soon as I lifted on that one, it broke right apart. Oh yeah, leads already fallen off of this one as well. I think we're going to have to grab our tweezers. There's the first. And there's the last one. I think what we'll do is just clean this up a little bit. There's a lot of residue on this board. Probably from the volatiles of the plastic cooking off. You know, really, other than this one through hole right there, heating up, doesn't look in too bad a condition. Alright, let's go ahead and we'll pull out these transistors. So we'll start with Q9. Again, as soon as I grabbed that part, it fell apart. Alright. And as a minimum, I'd say Q8 was stressed. I think we're going to go ahead and pull him as well. Actually, this Q8's the only one that came off in one piece. The other ones were cooked to the point where the leads fell off of them. And again, let's just clean that area up a little bit. Get a good idea what we're up against. Again, the traces look really good in this area. And the same thing up here. I don't see any damage at all to the circuit board. This is really the worst of it right there. Of course, we have the case, and you can see the damage from me pulling it apart. It basically melted and fused the plastic together. You can see it's no longer really a good fit. See how that plastic's already breaking out of there? I think the thing to do is just Go ahead and pull that. Even there, that area is pretty tight. See if I can get a knife, maybe we can break that piece out of there. It's done a very good job fusing that plastic together. There it goes. It should fit together really good now. Yeah, I think that's about the best we're going to be able to do with it. And I think the next thing I'd like to do is remove some of this old solder. And we'll try to remove the rest of it off of the back side here as well. Alright, all the solder's cleaned out of there. I think we're in pretty good shape now. If we look at the front end of this meter, basically following the normal input, it's going to run through these two sets of series PTCs and then into these MOVs, and then the two MOVs tie together and attach to a third MOV, which will again return to the common point. If we look at the ohms mode, for example, of course that's going to go to this function switch, and on the back side we've got our high-speed clamps. Of course, this is one of the clamps that we blew up with Q9, and then on the back side of this clamp it goes to R31, and then this goes on to U4. Let me just show you kind of what we're talking about. So it's going to run through the PTCs here, the MOVs are here, and it's going to end up on the back side of this switch at this point right here. From here it's going to make its way up to R31, which is this resistor here, and then this is going to make its way to U4. So this is our main controller, which is located underneath the LCD. Now if we look at the frequency input, again that's a similar type of input. That goes up to C16, and then on the other side of C16 we have this R19, and that's what's going on into U4. So I believe the value of this R31 and the fact that they have this R19, those may be enough to limit the current. So if I do expose the meter to ESD, it may actually survive. I don't know, again, we just have to try it. The problem that I've got, when I removed the display, fortunately I kind of rubbed it off here, but there was a little black splotch right here. Again, I just kind of rubbed it with my finger and it came right off. That black splotch is from this R19. So we've damaged this resistor. Again, the damaged resistor that we're looking at is R19. On the original UNI-T UT61, this would have been a 200 ohm resistor. Looking at the reference schematic for this IC, they're also showing a 200 ohm resistor. We'll go ahead and pull that out real quick. Again, this should connect to 65. In the lower left, this will be pin 1. 65 will be right around there. You can see it's definitely where it's going. This is the resistor we just pulled out. You can see it's reading roughly 2.3 meg now. Of course, it's got a hole in the back side of it. This is our new 200 ohm resistor. See 100 97 ohms. That's what we're going to put in the meter. And there's our new part. Next we'll go ahead and replace our transistors. Of course, I've transient tested both of my Brymen BM869S's, and one of the things I had done with this particular meter, after I had damaged it, I did a little research to try to find some better transistors. These are actually the original two that came out of this meter, and I bought some different parts that I thought may actually improve the meter's ability to handle some of these transients. And I can't remember what we took it up to, but I remember it was in excess of 10,000 volts, and the meter survived that just fine. Anyway, so what I'm thinking to do, this UNI-T meter uses a Y1 transistor for all four of these locations. We could substitute that with like a 2N222, or I could go ahead and try to get the Y1. But what I'm thinking to do, because I have, it looks like 6 of these left on the strip, and we only need 4 of them, we could go ahead and swap these in place of these 4. Of course, if the meter does real good with these transient tests, it could be because I'm using better parts than what the meter was supplied with. But I think what I'm going to do is go ahead and use these parts. Back into the bag for the next time we need them. Alright, so not the prettiest soldering I've done, but normally I do this under a microscope, so at least I'm not using that 100-year-old blowtorch like the last soldering I was showing you. Alright, that's it. We'll just clean up some of this residue. Still some plastic that was up underneath those mobs. So as we're cleaning things, we'll get some of this flux out from behind this spring. Looks pretty good. Alright, we'll make sure there's nothing on the lens. And then we can go ahead and reattach our display. Alright, let's just go ahead and put the meter back together partially. I'd say there's a good chance that the meter is going to be okay. Just the fact here that it's reading an open. Spring's still got quite a bit of flux around it. Clean that up. Clean up our battery contacts. Looks pretty good. Again, we'll reassemble back. Let's go ahead and turn it on real quick. And let's just switch it to ohms. Looks fine. Okay, we got to pop out the batteries. Just do a quick functional test. Again, we'll start off with the resistors. And again, this will be our 100 mega ohm. Getting slow, but looks really good. This will be our 10 mega ohm. Looks good. And here's our 1 mega ohm, 100K, 10K, 1K, 100, and 50. Again, let's just zero it out. And here's our 50 ohm. Again, let's go to continuity test. That looks fine. And let's go to diode. And this will be a single diode. And here's 2 silicon diodes in series. And let's go to capacitance. And this will be a 150 picofarads. This is a 1 nanofarad. Here's our 0.1 microfarad. Looks good. And again, this will be our 1 microfarad, our 10 microfarad, and this is our 100 microfarad. Then we'll go to frequency, and this should be 60 hertz. 60 hertz as well, 30 hertz. Let's just try it with our high voltage supplies, and this should be roughly 3 kilohertz. And you can see 3.02. As long as we're in this mode, let's switch it to DC. Again, this should be roughly 60 volts. And in AC mode, we should get roughly 70. Looks good. And if we want to go to AC plus DC, whatever good this does you, let's see if it'll track it. There's 58 and 66, 65. Yeah, again, not a very useful mode. And I doubt we did anything to damage the current input. We can give it a try real quick. So again, this will be our 100 microamps and 10 microamps and 1 microamp and 100 nanoamps. I think that's what we were reading before, roughly 120. So it looks like our meter is still functional. So I think before we hook this thing up to the transient generator, there's a few other tests I'd like to run with it. So after I buttoned up the meter, I went to hit the backlight, and I realized I had forgot to solder those 2 pins back on. So I had to take it back apart, resolder those, but yep, the meter's back together. I think that's going to be it for this video. Hopefully some of those experiments with the network analyzer answered some of your questions. In part 3, I'll start running some of my more normal tests. So that's all for now. Hope to see you on the next video. Till then, stay safe. Later.